We saw in a previous video that if A is the longest side of a right angled triangle, also known as the hypotenuse, and B and C are the shorter sides, then the square of the hypotenuse, A squared, equals the sum of the squares of the other two sides, that is B squared plus C squared. To prove this, we start by drawing a square. Then we pick any point on one of the sides of the square. The distance between this point and this point here will be one of the short sides of the right angled triangle. The distance between this point and this point will be the other short side of the right angled triangle. Next we take a compass and use it to construct four congruent triangles, right angled triangles, in the corners of this square. So we want the four congruent triangles to have a short side of length b, so I'll step off that distance and I'll mark it off up here. So this line segment here has a length of b. Now I'll do the same here and down here. Next we can draw in our four congruent right angled triangles. If I connect these 2 points together, we have a right angled triangle whose two short sides are B and C. The long side I will call A, consistent with the statement of our theorem. The long side is always opposite the largest angle in a triangle, the 90-degree angle in this case. So we just complete this to get four right angled triangles in the corners. Anyway, we know that the four triangles here have to be congruent because we have a side, angle and side the same in all four of them. So we have two sides the same, namely B and C, and the angle in between the two sides, the 90-degree angle, is the same in all four triangles. So if the four triangles are congruent, then the longest sides must be the same. So I'm calling the longest side of each triangle A. Its length is A units. So you see we have a quadrilateral in here, this diamond shape, whose sides are all equal. Now the angle that's opposite small c, this side here, I'm calling capital C. So this is the labeling convention that we use for trigonometry. Similarly, the angle that's opposite the small side B is denoted by capital B, this red angle, and the same for the other right angle triangles. Now angles B and C sum to 90 degrees. The reason is that the three angles in a triangle sum to 180 degrees. So if this angle here is 90 degrees, then B and C must sum to 90, so that we get 90 plus 90 equals 180. So if B and C sum to 90 degrees, what is this angle lambda in here, in the corner of this inner quadrilateral? Well, these three angles sum to 180 degrees. We have a straight line formed, so lambda must be 90 degrees. 90 plus 90 gives 180. Similarly, we can show that this angle is 90 degrees because the three angles up here make 180 degrees, and B and C sum to 90. Also this is 90 degrees and this here is 90 degrees. So the four angles are 90 degrees. That means that we have a rectangle. And since the four sides are the same, this rectangle is a square. Since we know the side of this square is the hypotenuse of each right angled triangle, we can get the area. So the area is just got by squaring the side, A times A, which is A squared. So the area of this white region is A squared. Next we are going to move two of these right angled triangles around. We won't take anything away from this white area. So this white area will always have an area of A squared. I will rotate this triangle up here in the top left corner through an angle of 90 degrees clockwise about this point here. So I'll select this object, select the point, and we want to rotate clockwise through an angle of 90 degrees. So this side of the triangle, which was once vertical, is now horizontal. So of course this angle here is 90 degrees. The length of this side here is of course C. What about this angle in here? Well, it's B, of course. I just mark it in here with the pen tool. This angle down here was C. I won't bother showing it the other way, I'll just use this tool. And of course this angle is 90 degrees. The white area is still A squared, of course. We haven't added anything to this white area. We've just shifted this triangle. So we haven't changed the size of the overall square. Now, you've probably guessed that we rotate this triangle here through an angle of 90 degrees anti-clockwise about this point. So this angle here was C. This angle here is B. Of course this is the right angle. B and C add to 90. Of course this angle next to the B and C is also 90. This line, this side of the triangle was once vertical, now it's horizontal. The short side of the triangle is of course B. Next we extend this vertical line to meet this horizontal line, this horizontal side of the square. So this here is a right angle. So notice this small quadrilateral up here, the four angles in it are 90 degrees. So it's a rectangle, and not only that, the sides are the same. Opposite sides of rectangle are the same, so if this is B, then this must be B. And of course this up here is also B. So the four sides are the same. We can get its area, we just square the side. So the area of this is B squared. So it's a square of area B squared. Now similarly with this rectangle here, well, it is a rectangle because all the angles are 90 degrees. Also this side is equal to this side here. So all four sides are equal to C. So the area of this square is C times C is C squared. So you can see that by moving the two triangles at the top, by rotating them down onto the two triangles at the bottom, we are left with two squares. The areas are B squared and C squared. And of course if we put these two squares together, we have to get A squared, because we haven't changed the white region. So A squared must equal B squared plus C squared. Of course, this proof depends on the fact that when we rotated the two triangles that were in the top corners, then they must fit down on the triangles in the bottom corners to form two of these two rectangles, these shaded rectangles. That happens because B and C add up to 90 degrees, and because the longest sides are the same. So A is the same in both triangles, so this triangle fits exactly on this, and we get B and C in this corner equals 90 degrees. We already have a 90 degree angle here, so we get this rectangle here. Similarly, we get a rectangle here. There's no gap left here because this line is horizontal, because it was once vertical, rotated through 90 degrees. It's horizontal with a length of C. This line here is also horizontal because it was a vertical line rotated through 90 degrees. So the total distance all the way across here is equal to C plus B, and that's equal to the side of the square. So these triangles fit snugly together. So we are left with exactly two squares of areas B squared and C squared.